right. So, in our course selected topics in decision modeling, we are in our 28th lecture. We are discussing constraint nonlinear programming, specifically on Karush-Kuntakar conditions. Is it all right? So, now we are in the middle of a problem that was an nonlinear programming with inequality constraints. So, in this particular problem, we have seen that two products are being produced, product A and product B, and a raw material is required for that, which is available around 40 kg, and the selling price is given as per a formula which is dependent on quantity, which is going to have an effect on non-linearity of the problem, and we have to determine the optimal quantity of product A and product B for maximization of profit. So, in our last lecture we have formulated the problem, and the formulation was like this: maximize function of x where there are three unknowns. The three unknowns are amount of product A in kg, amount of product B in kg, and the amount of raw material in kg. Is that all right? So, x1, x2 and not y1, that should be x3, right. So, these are the three unknowns, and the constraints were x1 plus x2 less than equal to x3, that is x1 plus x2 minus x3 less than equal to 0, x3 less than equal to 40, and all the variables greater than equal to 0. So, in our last class we have seen that this particular objective function is we found the Hessian matrix, and we found all the eigenvalues are either negative or 0. So, that means they are negative semi definite, and we can therefore conclude that the function is concave, and really speaking we can actually find out the optimal point for maximization. So, that much we have already seen in our next class. Now, in order to solve that, we should know at the optimal point, that is x equal to x star, this particular problem, I mean the variables should satisfy the KKT conditions. So, that is a necessary condition for optimality. So, let us see how to obtain the KKT conditions for this particular problem. Now, let us see that. So, the KKT conditions should be like this. Now, as I have shown you in the previous lecture, a simple way to interpret the first constraint is write out the Lagrangian function, the equivalent Lagrangian function for this, that is we have the f(x) which is equal to this, and we have g1x and g2x. Let us say we take two multipliers, the multiplier u1 for the first constraint and multiplier u2 for the second constraint, that is the g1x and g2x. Then the overall function lambda x L of x u1 u2 and x and u can write. So, which is nothing but L of x1 x2 x3 u1 u2. So, that is an total function that will be 170 x1 minus 2 x1 square plus 200 x2 minus 3 x2 whole square minus 100 x3 minus u1 x1 plus x2 minus x3 minus u2 x3, right. So, what we have done? We have combined the objective function and all the constraint into a single function. Now, we differentiate this. We take the partial differentiation with respect to x1, with respect to x2, with respect to x3. So, what will be the del L xu del x1? That is the first differentiation. So, that should be, first of all you see 170 as the first one, then 4 x1 that will get from this term. So, this term, these two terms are covered, 170 minus 4 x1, for the rest of the terms we will get nothing, and here we have minus u1 x1. So, if you differentiate we get minus u1, right. So, that will be the partial derivative of this total function with respect to x1, 170 minus 4 x1 minus u1. So, just look, that is precisely written 170 minus 4 x1 minus u1 less than equal to 0. So, that is the first condition that we obtained by differentiating this function with respect to the x1. Now, if you differentiate with respect to x2, then you see what are some x2 terms, 200 x2. So, 200 if you take partial differentiation, minus 3 x2 whole square. So, minus 6 x2, and any other term here, that is minus u1. So, 200 minus 6 x2 minus u1 less than equal to 0, that is the second term. So, what will be the third term? Differentiate with respect to x3. So, that is minus 100, and this is plus u1 x3. Can you see that? So, if you differentiate it will be plus u1, and if you differentiate minus u2. So, minus 100 plus u1 minus u2 less than equal to 0. So, I hope you have understood that how we really obtain this. Otherwise, what you can do, you can differentiate f(x), we can separately differentiate g1x and g2x with respect to x1, x2 or x3, and then combine them by taking the appropriate multiplier. But anyway, if you feel this method is simpler, then you can use. And obviously, how to combine the f(x) and g(x), whether to use plus sign or minus sign. For maximization problem we usually use minus sign, and for minimization problem usually we use plus sign, but then various books may have other kind of conventions. So, if you look in our one of our previous lecture, we have taken plus sign when in a minimization problem. But since the ui's are all scalar values, even if you take another sign, ultimately it will be done by the negative value of u's that we obtain. But it will not be possible in KKT conditions, because we have strict conditions that all ui's should be greater than equal to 0. So, we have to take the negative sign by making the problem as one of maximization, right. So, this must be remembered that here you cannot substitute these so, when you take the total function L x u equal to f(x) minus u1 g1x minus u2 g2x. So, here this minus sign has to be always taken, right, you cannot do something else. Fine. So, so far we have seen how exactly we take the first condition converted to a set of KKT conditions. Now, let us take the second one. The second one is very simple. It is the first condition part only, that is 170 minus 4x1 minus u1 multiplied by corresponding variable. So, x1 into this equal to 0, x2 into this equal to 0, and x3 into this equal to 0. So, these are the first two KKT conditions, right. Now, the third one is very simple really, it is the constraint itself. So, what was the constraint? x1 plus x2 minus x3 less than equal to 0, and this written in this way, x3 minus 40 less than equal to 0. So, this is the third constraint. The fourth constraint is that the corresponding multiplier and this term when you multiply that should be equal to 0, right. I am not telling this here, but this has the similarity with the duality constraints in linear programming, right. Now, in duality they have these complementary slackness conditions which essentially says that either the primal equation will turn to equality or the dual variable should become 0. So, anyhow, if the primal equation turns to equality, then the dual variable exists, or if the primal slack exists, then the dual variable will not exist. But anyhow, it is a similar condition like this, but then that is not exactly what we are discussing here. So, same thing here. So, either these slack will vanish from this equation, that means this will become 0. In other words, x 1 plus x 2 should be equal to x 3 and x 3 will be equal to 40, or the corresponding multiplier should be equal to 0. So, these are the third and fourth constraints. The fifth and sixth constraints are very straightforward, that is these variables x 1, x 2, x 3 and the multipliers u 1 and u 2 should be all equal to zeros. So, that is all our KKT conditions. So, all the KKT conditions are put here. Once again, if you see, so these are from partial derivatives. These are that either the this equation will turn to equality or the corresponding decision variable should be equal to 0. These are the constraints themselves, not the objective function, and this is either the constraints will become equality or corresponding multiplier should be 0. So, those kind of constraints, and finally, these are the non-negativity constraints. So, these are all the KKT conditions. Now, the question is that as I have told earlier that really speaking here all the x variables like x 1, x 2, x 3 are really the very important point, let me write that all of these constraints, all of these decision variables are at the point of optimality, right. This point has to be very importantly remembered. That means that really speaking we are really talking about x 1 star, x 2 star and x 3 star, right. That is the optimal variable values. That means the KKT conditions are true at the point of optimality. This point has to be remembered. So, as I have not written, but really they are all actually all these x 1, x 2, x 3 are nothing but x 1 star, x 2 star and x 3 star, right. The question is how do I solve this? I have all these conditions, so many of them. Question is how to solve. See, this itself is a challenge in itself. Really we are not going to go very much into it, because today most of these problems after you obtain the conditions are to be solved by computers. So, probably you can make use of computers and software packages to really solve this problem, but for simpler problems such as this we can solve by a method of inspection, right. So, I will present an inspection method of really solving this. So, let us see how we can solve this by a method of inspection. So, first of all, by the nature of the problem x 3 cannot be 0, because look here we have a constraint x 1 plus x 2 minus x 3 less than equal to 0. So, if x 3 equal to 0, automatically you see we have a constraint that x1 plus x2 less than equal to x3. If you recall, x3 is the raw material. So, if the raw material is 0, we have no raw material available. What does it mean? It means x1 and x2 cannot be produced because there is no raw material. So, they also will become 0. Now, if everything becomes 0, the problem is trivial. That means the problem vanishes. That cannot be the optimal point. So, this therefore, we can say that x3 will not be equal to 0. Is all right. Now that we know x3 is not equal to 0, so look at this third constraint, 2c, constraint 2c, x3 is not equal to 0. So, if x3 not equal to 0, which means what? That means this term should be 0. That means minus 100 plus u1 minus u2 should be equal to 0, right. So, this equal to 0, that will give u1 minus u2 equal to 100, right. So, u1 minus u2 should be equal to 100. So, although it is not really just we cannot jump like this. So, we can say a possible solution for this could be u1 equal to 100 and u2 equal to 0, right. Let us go ahead with this and see if I take these u1 and u2, can we solve all of the constraints. So, precisely that is what we are going to try, that we take u1 equal to 100 and u2 equal to 0, right. So, these two we take. Now, if we take this, if you see that 170 minus 4x1 minus u1 is less than equal to 0, if you take u1 equal to 100. So, that means 170 minus 4x1 minus 100. So, this is the question constraint 1a. So, what does it mean? It means that 70 minus 4x1 should be less than equal to 0. So, in other words, see, let us write it, 70 minus 4x1 less than equal to 0. Now, just assume x1 equal to 0. If x1 equal to 0, then 70 should be less than equal to 0, which is cannot be. So, therefore, you know, x1 greater than equal to 0. So, because look here, x1 is greater than equal to 0, but x1 cannot be 0. So, x1 is greater than 0. So, really speaking, we have proven x1 equal to 0. So, x1 not equal to greater than 0. So, now look at constraint 2a. The 2a says x1 into 170 minus 4x1 minus u1 equal to 0. So, x1 is greater than 0, right, it is a non-negative or non-zero. So, automatically that means this second term should be equal to 0. So, you see therefore, 170 minus 4x1 minus u1 should be equal to 0, but u1 is 100. So, x1 is 17.5, right. So, this is how we can solve x1 for these values. Now, similar logic can be given for 1b and 2b, right. So, if you look at 1b and you put u1 equal to 100, so 100 minus 6x2 less than equal to 0. So, x2 cannot be 0. If x2 equal to 0, then 100 should be less than equal to 0, that is impossibility. So, therefore, x2 is greater than 0. Now, look at constraint 2b. So, this is constraint 2b, x2 greater than equal to greater than 0. So, that means if these two terms should be multiplied as 0, so 200 minus 6x2 minus u1 should be equal to 0. Now, 200 u1 is 100. So, 100 minus 6x2 equal to 0. So, what will be the value of x2? The value of x2 will be 100 by 6, 16.67, is all right. Now, similar logic can be given in 4a also. Look at 4a, u1 into x1 plus x2 minus x3 equal to 0. Here u1 is greater than 0. So, you know, we get x1 plus x2 minus x3 equal to 0. or x3 equal to x1 plus x2 equal to 34.17, right. So, we have got all of them, that is x1, x2 and x3 values. So, we found that these set of solutions, that is x1 u1 star equal to 100, u2 star 0, x1 star 17.50, x2 star equal to 16.67 and x3 star equal to 34.17. They are actually solutions which incidentally satisfy all the KKT conditions. But see, look here, we have really not solved the problem, we have obtained them by inspection. So, since we have obtained by them by inspection, we should ensure it further. So, like if you try to ensure, if you put x1 star 17.5 and u1 equal to 100, you see that this becomes 0. So, it is satisfied. Second one is also satisfied, third one yes, next 3 yes, this one yes, this one yes, this one u1 is 100 and this one is 0 yes, u2 x2 equal to 40 yes, that is also yes. So, that means all the conditions are satisfied. That means this trial solution really satisfies all the KKT conditions, right. So, we have also seen in our previous lecture that the function is concave. We obtained Hessian matrix and we saw that they are negative semi definite. So, combining these results, we can say that this is our optimal solution and the objective function comes out to be 1445.83, right. So, we have solved this problem. So, in the remaining time, let us quickly check one more problem just for confirmation of our ideas, and we shall see how to quickly really solve such problems. Supposing I have a problem taken from Hillier and Lieberman book, f(x) equal to ln x1 plus 1 plus x2 subject to 2x1 plus x3 less than equal to 3, x1 less than equal to 0 and x2 less than equal to 0, right. So, we have one functional constant and it is a convex function. Why? Because it is linear. So, necessary conditions requires that f(x) should be concave for a maximization problem, right. So, it is so that this is a concave function, we are not proving it, but we know that yes it is. So, therefore, the sufficient condition is taken care of, the concave objective function and convex functional constraint. So, if we find a solution that satisfies the KKT conditions, that will be optimal. Is it all right? So, that is the starting point. So, let us see how we obtain the KKT conditions. So, this is if I combine the two, then again we have L x1 x2 u1 equal to ln x1 plus 1 plus x2 minus u1 2x1 plus x2. So, this is the combined function. So, if you differentiate with respect to x1, so that is del L del x1 equal to ln of this function. So, 1 by x1 plus 1, that is the partial differentiation, this term will give nothing and this term will give 2 u1. So, that is the first condition. So, this is the del L del x1. What is del L del x2? Del L del x2 will give, this term will give nothing, this term will give 1 and this term will give minus u1, right. So, that is the second condition. So, these are the second two conditions are identified. from this we find x1 into this term, this is, and x2 into this term, they are equal to 0, is it all right. So, this is how the second condition can be obtained also, that is x1 into this and x2 into this. So, that is the second conditions. The third condition can be obtained by the constraint itself, right. So, what is the constraint itself? That is 2x1 plus x2 minus 3 less than equal to 0, that is the third constraint. And what will be the fourth? Fourth is multiplied by the multiplier should be equal to 0, and then fifth and sixth conditions will be that all these terms should be non-zero. So, non-negativity constraint, right. So, we have obtained all the 6 KKT conditions, and those 6 KKT conditions can be written here. So, I have written all the KKT conditions. So, these are all the KKT conditions. All the KKT conditions. So, look here, 1 plus x1 plus 1 minus 2 u1 less than equal to 0, x1 into this equal to 0, 1 minus u1 less than equal to 0, that is x2 into 1 minus u1 less than equal to 0. Yeah. And then, so that is the second part, that is del L del x2, and 2x1 there is a constant itself. This is the multiplied by the multiplier, and these are the non-negativity constants. So, all the KKT conditions will be written on one side. So, now we can see them, then how to solve this problem. So, first of all we have to really find out a set of solutions, then see now again we are solving basically by inspection. So, there is logic you have to find out. Really speaking, here some logic is given, but it does not mean that this logic is universal and all problems similar logic will hold, right. So, really solving this problem from this point onwards basically is a task, non-trivial task. We have this constraint, we have to really obtain a set of values x1, x2 and u1 which will really give a solution. So, a quick solution we are just trying out, nothing else. So, step 1, if you look at 1b, then you see u1 should be greater than equal to 1, right. So, this is what you find, and so see if I see this constraint and if I see number 5, that is x1 should be greater than equal to 0. So, we see that u1 is greater than equal to 1 and x1 is greater than equal to 0. So, suppose I put u1 equal to 1 and x1 equal to 0 in 2a. So, this is 2a. So, put x1 equal to 1. So, x1 equal to 0 and u1 equal to 1. What you get? You get 1 by 0 plus 1 minus 2, right. So, you see these are like floor values. So, if I put floor values, can you see that this is negative, right. So, you see in 2a, by putting u1 equal to 1 and x1 equal to 0, I find that this value which is within the bracket is actually negative, right. So, it actually is negative. So, now any x1 value higher than 0, right, and any u1 value more than 1 will be even worse. So, basically as long as these two conditions are satisfied, that is u1 is greater than equal to 1 and x1 is greater than equal to 0, this term will be always negative, right. This term will be always negative, because the lowest values itself it is negative. So, any higher value of x1 will become, this will be even lower, and any higher value of u1, this value will be even higher. So, this will be always negative. So, that is what we found out at step 2, that this is negative. So, if this is negative, that means non-zero. So, 2a says x1 should be 0 then, right. So, x1 should be equal to 0, also u1 is greater than equal to 1. So, that means u1 should not be equal to 0. So, now look at the fourth condition, u1 is not 0, that means 2x1 plus x2 minus 3 equal to 0, right. So, we get these facts that x1 equal to 0 and 2x1 plus x2 minus 3 equal to 0. So, what does it mean? It means x2 equal to 3. Why? Because x1 equal to 0. So, x2 should be equal to 3, right. So, that is how we have been able to obtain a trial solution. So, we have seen x1 equal to 0, we have seen 2x1 plus x2 minus 3 equal to 0. So, we have x2 equal to 3 and we already seen u1 equal to 1, right. So, since x2 not equal to 0, so we can take this condition we can take x2 not equal to 0. So, if x2 not equal to 0, then u1 should be 1. So, all the KKT conditions are now satisfied with x1 equal to 0, x2 equal to 3 and u1 equal to 1. Is it all right? So, the optimal solution will be then x star equal to 0, 3. So, anyhow in this lecture we have further seen how to solve problems by making use of KKT conditions, right. So, in our subsequent lectures we shall see more examples on nonlinear programming problems, right. So, thank you very much.